Lesson 11.4, Finding Sums of Infinite Geometric Series. All right, consider this whole grid. If I take half the grid, it's 0.5. If I take half of the remaining half, that's a quarter of it. So a half plus a quarter is 0.75. And if I do half of the black part, so half of the half, that's 1/8. Add those together, I get 0.875. If I add half of what's left, so that would be half of a half of a half of a half, or a 16th, get 0.9375 if I add the whole colored area together. And then, well, let's add half of what's left. Half of a 16th would be a 32th. So a half plus a quarter plus an eighth plus a 16th plus a 1/32. It's 0.96875. And I add a half of what's remaining, which would be, what, a 64th? So I have a half plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64th. What's going to happen if I continue this pattern forever? Well, eventually the entire thing's going to fill in, because next it'll be that, and then that, and then that, and that, and that, and that, and that, and that. If I go forever, eventually it'll be all filled in, and the total area will be 1. All right, so let's kind of do the same idea here. Find the partial sums for n equals 1, 2, 3, 4, and 5, and describe what happens to the sum as n increases. All right, so a partial sum is adding the first term. Well, that's easy. It's a fifth. S2 is adding the first two terms. A fifth plus a tenth is 3/10. So that was 0.2. This is 0.3. S3 is adding the first three terms, which gives us 7/20, which is 0.35. S4, add the first four terms, which gives us 15/40, or about 0.375. S5, add the first five terms, you get 31/80, which is 0.3875. So now look at the pattern of the sums. What's it approaching? It looks like we are approaching (0.4). Why don't you try number 3? When you're finished, Sn approaches 10. All right, the sum of an infinite geometric series. Well, the sum of a geometric series was that. However, if n becomes very large, let's consider that if r is a fraction, like a half, let's let r be a half. A half, let's say, squared is a fourth. A half cubed is an eighth. Half to the fourth is a 16th. You can see it keeps getting smaller and smaller and smaller. So a half to the infinity is approximately 0. So that would become 0. And our sum would simply become a1 times 1 over 1 minus r. or a1 over 1 minus r. But that's only if the absolute value of r is less than a 1. So it has to be essentially between 0 and a 1. If r is greater than 1, then there is no sum. All right, find the sum of that one. Well, first of all, how do we know it's geometric? We know it's geometric because it is exponential. The variable is in the exponent. We compare this to a(n) equals a1, r to the n minus 1. You can see a1 is 2 and the r is 0.1. Since it's infinite, the sum of an infinite geometric series is a1 over 1 minus r. a1 is 2, r is 0.1, so that's 2 over 0.9. I don't want a decimal in my fraction. I'm going to multiply the top and bottom by 10. Gives me 20 over 9. Why don't you pause this and try number 9. Now this is interesting here. Consider this as 2 over 1. Therefore, it looks like we are multiplying by the top by 3 and the bottom by 4. And a1 is 2. So plug it into the formula. You should end up with 8 for your sum. A pendulum that is released and swings freely travels 100 centimeters on the first swing. On each successive swing, the pendulum travels 90% of the distance of the previous swing, so it's slowing down a little bit. What is the total distance the pendulum travels? Well, first time is 100 centimeters, and the next time is 96% of that, so our r is 0.96, 96%. And we want the total distance, so we want r infinite, which is a1 over 1 minus r. So it's 100 centimeters over 1 minus 0.96. Or 100 divided by 0.04, which gives you 2,500 centimeters, which, if you're curious, is going to be 25 meters. Another application of the infinite sums is to write repeating decimals as a fraction. Notice it repeats. The 2,7 repeats. So what we're going to do is we're going to write the repeating unit as a sum of fractions. So the first 27 is 27, and it's in the hundredths place. The next 27 is 4 digits in, so it's in the 10,000ths place. The next 27 is 6 digits in, so it's in the millionths place, and then the 100 millionths. All right, so this is a infinite geometric series. A1 is 27 over 100. R, well, we're multiplying the top by 1. The bottom we appear to be multiplying by 100. So it's a1 over 1 minus r for infinite geometric series. a1 is 27 over 100. R is 1 over 100. One minus 100th would be 99 hundredths. Divide fractions by multiplying by the reciprocal. In this case, the hundreds cancel, and I have 27 over 99. We could reduce those by 3. By 9, actually. 27 divided by 9 is 3. 99 divided by 9 is 11. So it is 3/11ths. Now I know you know other ways of doing this is getting that repeating decimal as a fraction, but please practice the infinite geometric series and do it this way for this lesson. All right, why don't you pause this and try number 21. 32 plus 32 over 100 plus 32 over 10,000 plus 32 over a million. All right, so A1 is 32. R appears to be, this is like 32 over 1. So the top we're multiplying by 1, the bottom we're multiplying by 100. So our formula is 32 over 1 minus 1/100th, so it's 32 over 99 1/100ths. Multiply by the reciprocal gives you 3,200 over 99, and we cannot reduce that.